Have you heard of this concept before? It's a very powerful concept. It's a sort of method when you associate a number to a matrix, and just by looking at this single number, you can discover some properties of the behavior of the matrix itself. So I'll give you some just like what it is first, and I'll give you some examples how we compute that. It's another computationally intensive process because it's tightly connected with the inverses, in fact, determinants, and because the inverses is something which is difficult to compute, the determinants also, by implication, is something which is difficult to compute. But the way we compute them is very like a structured way. Look at this actually. So when you go for the determinants, you can always do that for square matrix. I'm not sure if I used this notation before. When I put this like next to my class of matrices, I just emphasize that matrix has complex entries. In this case, I mean, like you can compute determinant, in fact, in principle, for any matrix with complex entries. Although most of the time you will look at the real numbers, but there's no difference between complex or real entries. So notationally, it's something like this. You either write det A, which stands for the determinant of the matrix A, or you put sort of absolute value around this A. This is just a notation for the determinant. The result of that, it's a number. So look how we compute this number. We compute this number recursively, depending on the dimension of the matrix, depending on the size of the matrix. The easiest one, of course, when the matrix of size 1. The matrix of size 1 is just a number, one single number, in which case the determinant of the single number is just the number itself. Now, when you look at the size 2, here you will have a direct formula. Look at this. If you have a matrix, 2 times 2 matrix with arbitrary entries, look what you do to compute the determinant. I'll give you the formula, and I'll explain the structure in a second. The formula looks like this. You multiply first the elements across this diagonal with each other, and then you subtract the product across this diagonal. That's how you compute the determinant of 2 times 2 matrix. You multiply across this diagonal, A11, A22, and subtract across this diagonal. Now, when you go for free, that's where the recursion, or the recursion starts appearing. Look what you do when you go for free. Here's the general matrix of size 3. So all 3 elements, all 9 elements, indexed with the row and the column index, all of them, all 9 of them. Look what you do. You take the first row, this one, and you do this sort of mental procedure with it like this. I'll make this little picture, which will help me to do that. You single out the first element in the first row, you cross out everything underneath, you cross out anything to the right. The remaining numbers, they form a smaller matrix or a smaller determinant. And you put here this element A11, which is circled out here, and next to it you put the determinant of this remaining 2 times 2 block, the one which is left after I cross whatever is here shown, crossed out. Now, you do it for every element in the first row. So you take this thing and you now look at this element. This crosses out this element, and this one. The remaining ones, these 2 together and these 2 together, will be another smaller determinant. You will look at this. This is the element, and that's the smaller determinant, which is left after I crossed out the elements with these blue lines. Another thing which you have to pay attention to, we have a negative here rather than the positive. The final element, when you take this and you look at this element, again, you take the element A13, here it is, and you multiply by the smaller determinant, which is remaining here, this one. Here it is. Again, it is impossible to remember this in the symbolic form, but it is quite possible to remember the process. And I won't be doing this crossing like this visual. I won't be visualizing this crossing every time we do the determinants, but I will be visualizing in my head, and I'm hoping you will be doing that. You will be doing the same in your heads. Again, you take the first row, you take the elements of the first row, first element, second element, last element. You alternate the signs in front of those elements. This one comes with plus, this came with minus, this came with plus, and you factor them with the determinants which are left by crossing things out like this. That's for the first one, that's for the second one, that's for the last one. And that's the sort of recursive definition, because the determinant of size 3, when you compute it, it relies on determinants of size 2. These blocks, all of these 3 blocks, you have to compute them according to this formula. Okay? You can do the similar procedure with the, actually you have to do the similar procedure with the matrices of higher size. So I'll give you the general look of it, like for the matrix of n times n. You don't have to copy that, it will be like in the printout. You have to remember the structure. That's the main thing here, and we will practice this on the next slide. So if you have a bigger matrix, like a huge matrix of n times n, here it is. Let me just open all of it. So you take this element, it's not big enough, let's just make it, almost reaches up to the end. So you're crossing everything out in the first row, and you take this element, and you multiply this element with everything which is left. I didn't copy this everything which is left, but I have this capital A11, which symbolizes the determinant of size n take 1, so of smaller size, which is here. Now you take the next element in the row, you cross out the row, you cross out the column, the remaining bits, they will compose a determinant of a smaller size, n take 1 size, and that will be the element which will appear next. A12, alternating signs, and then A12 capital. It's something which I use to abbreviate for this smaller determinant. You do it for every element. For instance, this element, for every element in the first row, you will do that. And you will have this expansion. And this you see -1 to the power n indicates this alternating signs you do all the time. Now for every of these a's, it will be smaller determinants for each of those. You have to do the same crossing out procedure. It is a long process. That's why we're not going to give you high metrics of the large size. 4 probably will be the highest, unless there is some effective way to avoid this. We will study some properties of the determinants, which will let you sometimes do shortcuts, very effective shortcuts, but in principle, that's how you compute the determinant of matrix of arbitrary size. Let's just practice this. Well, actually, I have this piece of a terminology for you. These elements, AJK, they call JK minus. It's just a term which Yellow Book might use sometimes. These smaller determinants, which you come up with by crossing out the column and the row, they call the minors, or the JK minors. It's just a name.